In this video, I'll be talking about volumes of rotation. And notice we will have two different forms. We will have a disc, and then we will also have a washer. And the main difference between these two, the washer will be the one that has this opening whenever you're revolving. And so you do end up with this washer looking shape, whereas your disc formula does not have any holes in it. Our axis of rotation and the bounded region are flush with each other. So let's look at number 1, and it would start off to be a good idea to sketch the regions given. And so we have y equals 0, that's going to be our x-axis. We also have the line y equals x, so we'll be sketching y equals 2x, sorry. So we'll be sketching that, and then we will also have the line x equals 3. So we'll also have that region to sketch. So we should have something that looks like this. Now it is a good idea to find your point of intersection here. So that point there is going to be where my line y equals 2x and x equals 3 cross. So that ordered pair should be 3. And then if we plug in that 3, we're going to get 6. So there's our ordered pair. Now we do need to imagine this bounded region that we have here. And we are going to rotate this about the x-axis. So if we do that, we should have this nice solid that is formed whenever we rotate. And notice that you're going to have this full cone looking shape here. So as far as needing a disc or washer, this is just going to be a disc. And so I just need the radius of that disc. So there would not be a little r value. And the radius, that's going to be the distance, the longest distance from my function to the axis of rotation. So that's going to be this portion here where we have that line, and then we have our bottom portion here, our axis of rotation. So that distance would be this top function, which is 2x, minus the bottom, which is 0. So our big R is just 2x. And so to find that volume, we're going to have pi times the integral of just that big R squared. So 2x all squared dx. We do need to consider what our endpoints would be. And since we are rotating over the x-axis, then we need our x values. And we would have started here at 0, 0, out to 3, so we are integrating from 0 to 3. The final answer on that should be 36 pi, and I'm going to leave that for y'all to show. Okay, now moving on to our next example, we're going to have the same exact shape, but now we're rotating about the line y equals 6. So we're going to take that same shape that we had, and I'm just going to resketch it over here. Our XY axis, and we still have the same functions that we're using, so I'm just going to do a little partial sketch here of what we were given. And again, that point of intersection there was 3, 6. And now we're going to revolve this about the line y equals 6. So that's kind of handy because it's going to go through their point of intersection. So now we've got our new axis of rotation here, and we see that we have our bounded region again, and that bounded region is going to be sitting inside here. There's that bounded region. And so we need to take this and we need to revolve it about y equals 6. Well, if we do that, notice we are not sitting flush with our axis of rotation. So when we do this revolving, we are going to end up with something that kind of looks like this. We're going to have a solid portion here, but then we're going to have all of this open area here. And so we're going to have to somehow remove that. That's why we need our little arm. So the big R, that's going to be what we need for the entire distance. So that's going to be from our axis of rotation to the very bottom portion of our bounded region. So that portion there is going to be from my axis of rotation, which was y equals 6, all the way down here to the bottom, which is y equals 0. So that distance there from 0 to 6 is 6. So there's our big R. Now little r, we're going to have to label that for the portion that we are removing, that's generating this open area. And that distance there is going to be what's going on between our axis of rotation and our bounded region. So here we have y equals 6 is the top, and then the bottom was our function 2x. So our little r, or the area that is needing to be removed, is going to be 6 minus 2x. And so now we have our volume, pi, is going to be integrated from, again, we are staying parallel with the x-axis, so use your x endpoints. We're going from 0 to 3, and then we're going to have big R squared minus little r squared. And if you choose to work this out, it looks like you should have 72 pi for an answer. Okay, for our next problem, again, very similar. We do need to sketch what we're given. And then this one, our axis of rotation is going to be up at y equals 8. So again, I'm going to just sketch that general shape that we had. I know their points of intersection here is 3, 6, but now my axis of rotation has been moved way up here to y equals 8. So we're taking this full bounded region here, and then I'm going to rotate it way up here. So it's almost like you're going to have a huge cylinder in between your rotations. It's going to have a big gap in it. And so let's talk about our big R value. Well, your big R is going to have to encompass every bit of it. So that total distance from y equals 8 is all the way down to the x-axis, which is y equals 0. So that distance is 8. But then we need to come back and take out the inner part, or the part that's creating the hole in the graph, which is going to be right here, or hole in the revolution, sorry, or solid here. So that's going to be 8 minus 2x. So the volume is going to be pi, and we are integrating. Again, we're parallel with the x-axis, so use your x coordinates, so 0 to 3. And then we're going to have our big R squared minus the little r squared. And again, if you finish that out, you should have 108 pi. All right, moving on to the next part, we are now going to use all the same stuff, but I'm now going to revolve this about the y-axis. So that's going to change a few things. One thing, we still have our same basic shape. However, we are going to have to change how we're referring to this, because again, we're going to be going with the y-axis. So again, same basic shape, and here's our solid, and our point of intersection is 3, 6, but this time I'm wanting to revolve it about the y-axis. So really we need to change everything to talk about y, including our original function. So our original function was y equals 2x, but if we're dealing with the y-axis, we need to make this say x equals. So I'm going to divide both sides by 2, so I know y over 2 is going to be equal to x. And again, we're just changing this to be in terms of y simply because we're revolving about the y-axis. Now, something for us to notice is we are not flush with our axis of rotation. So we're going to probably have a small r in this. So let's look and see. And keep in mind, this line here, that was x equals 3. This line over here, or the y-axis, is x equals 0. So if I want to find the entire area, every bit of it, that's going to be the distance from 0 to 3, or the big radius is 3. For the little radius, or the part that is causing us to have a hole when we do our rotation, then that's going to be coming from here. This is going to be our small radius, and that's going to be the distance from here. Instead of saying 2x, we need to say y over 2. That was that function, all the way to x equals 0. Well, then that distance is just going to be y over 2. Or y over 2 minus 0, but you definitely don't have to write that 0. So now we're ready to fill in our formula. We have the volume equals pi. We are integrating, but now we're going parallel with the y-axis, so we need to use our y-coordinates, which is going to be from 0 all the way up to 6. And then we're going to have our big R squared minus the little r squared. And then we're going to say dy. Alright, let's take the same information again and let's repeat it for these other two lines. So again, we're going to sketch our x and y axis. And again, we're going to keep that same shape that we've been working with and the same points of intersection here. And I'm just going to fill in our area here. Okay, our axis of rotation for this one is actually one of the sides of our solid that will be revolving. So x equals 3. And if we revolve this, notice we are flush with our axis of rotation. So we will not have any gaps when we do our rotations. So there'll be no little r. But the big R, the region that we are rotating, will be from x equals 3 over to x equals y over 2. And so that distance there would be 3 minus y over 2. And so our volume would be pi. And then our limits of integration, since we are parallel to the y-axis, we would be going from 0 to 6. And then big R squared, so 3 minus y halves all squared dy. Alright, so now moving on to a letter F. Again, more of the same, so we're going to go ahead and sketch our same solid region. Again, we have this region here. We have our points of intersection here at 3, 6. But now we're going to be rotating about the line y or x equals 4. So we're definitely going to have a cylinder of such in between this. So we have here again x equals 4. So we're going to have this huge gap in between whenever we do our rotations. So again, hopefully we can picture what's going on, because I certainly can't draw it, and that's terrible. We're just going to remove that. Anyway, so in our big R, little r, we need big R to represent every bit, everything. So we're going to go from here all the way back over to our other function. So that's going to be from x equals 4 all the way back over to x equals y over 2. And so that distance would be 4 minus y over 2. That's going to get everything. And then we need to come back and subtract out the small r, or the portion that is creating the gap, and that's going to be right here. So that distance is going to be 4 minus 3. And now we have our volume is going to be pi times the integral, and again we're with the y-axis, so we're going to say from 0 to 6, and we're going to have big R all squared minus little r all squared, and then dy because we are in relation to the y-axis. Right, in example 2, again, we are going to do a quick sketch of our given information, and we are told that we have y equals x minus 1. So we're going to have this line here. And then we also have the line y equals 0, which is going to be our x-axis. And then we have x equals 3, so we're going to have this portion here. So it looks like we have another bounded region that looks like a triangle. And so it's a good idea just to go ahead and find that point of intersection for these. So I need to find where the line y equals x minus 1 intersects with x equals 3. Well, that's pretty easy. We're just going to plug in 3 and we're going to get a 2. So we found that point of intersection. And so now let's go ahead and talk about our revolving about the x-axis. So we're revolving here, and that is flush with our axis of rotation. It's one of the sides, so that tells me quickly that I'm not going to have a little r. And with big R, again, we need to define that radius that we're going to have for the washer. And so notice that radius is going to be from our function down to the axis. So in other words, that top function is y equals x minus 1. The bottom is y equals 0. And so that distance, or the difference between those, would be x minus 1. So now we're ready to set up our volume. We have pi, and we're going along the x-axis, so we need to use our x-coordinates. Now be careful, it's not at 0 anymore, it's at 1. So we're going from 1 to 3. Almost said 2 there. Let's erase that. 1 to 3. And it's just going to be our big R squared. And if you want to go ahead and find that volume, then you should get 8 pi over 3. All right, so looking over here at our next example, again, we still have the same bounded region. So again, these problems very similar. And we're still going to have here at 1, and then we're cut off here at 3. We have the same bounded area here, and we are intersecting at the point 3, 2. And now we want to look at revolving this about the line y equals 2. So we're looking here. This is our axis of rotation. We always have to stay in relation to that. And notice we are not up against or flush with our axis of rotation, so we know we're going to have a small r. Big R is going to be the distance from our axis of rotation to that bottom bound, which that bottom, remember, is y equals 0 there. So we're going to say 2 minus 0, so big R is 2. That's our big radius. And then for our short radius, then we've got to figure out, well, what's going to be causing the empty spot. And that's going to be from our axis of rotation to our closest function, which is right here. And so that's going to be 2 minus, and then our function was x minus 1 there. So now we're ready to go through and do our volume. We have pi. We're integrating from 1 to 3 of big R squared minus little r. So that was 2 minus x minus 1 all squared dx. And again, if you work that out, you should have 16 pi over 3. All right, moving on to C. Again, very similar. We're going to do the same sketch. Oop, I almost went through 0, 0. We're not going through 0, 0 this time. Same bounded region here. Same point of intersection is 3, 2. But now we want to go our revolution to be about y equals 3. So that's a little bit above here. And so here's our axis of rotation. Always stay in relation to that. And now let's look and see what's going to be the longest distance. And again, that's going to be from y equals 3 down here to y equals 0. So that's going to be every bit of it. So that distance is going to be 3. And now we need to find little r. And again, I know little r exists because my axis of rotation and my bounded region is not flush. So here we're going to be from here to here. And so that's going to be from 3 down to my function, which was x minus 1. And again, we're ready to go through and set up our volume. It's going to be pi times, and again, we're parallel to the x-axis, so use your x coordinates, so 1 to 3. And you're going to have your big R squared minus your little r squared, so 3 minus x minus 1, all squared dx. All right, moving down to the next one, and now we're going to be talking about in terms of y. So we need to rearrange before we do anything. Of course, the shapes are going to be the same, but originally we had y equals x minus 1. So we need to make this say x equals y plus 1. But nothing else would change. Again, we still have that same bounded region that we've been working with. And here our point of intersection is still at 3, 2. And here at 1 there. But now this time, notice we are going to be rotating about the y-axis. So that y-axis is my axis of rotation. So now it looks like we're definitely going to have a little r with this. Now we just need to find it. All right, so our big radius is going to be all of this area here. So now we're going from x equals 3 all the way back over here to x equals 0. That's going to be every bit of it. That's all of it. So then that region, or big R, is going to be 3. Now let's look for little r, our small axis, or our small radius, sorry. And that small radius is going to be here, which function is closest to your axis of rotation. So here to here, so that distance is going to be y plus 1, because we do need to rewrite it. So y plus 1 all the way over to our axis, which is 0. So now we're ready to find that volume, but this time our limits of integration need to follow along the y-axis. So that's going to be from 0 to 2. And then it's going to be big R squared minus little r squared. Right, now let's go ahead and see if we can do a couple more of these. And again, we're still going to have that same basic shape. And now we're going to have a different axis of rotation though. We have this, and then we also had, what was the other portion here? And we have that point of intersection was at 3, 2. But now we're going to have here at x equals 3 is going to be our axis of rotation. So again, we are flush with that axis. So if we revolve around this, then we're going to form a solid. So there will not be a small r here. We're just going to have our disk. And so let's see, our big R, again, we need to change this though. We need to do the x equals y plus 1. And so the big R that we need is just going to be from here to here. So we're going to have from our axis of rotation to our function. So from right to left, that's going to be 3 minus y plus 1. And again, we don't have a little r, so we're ready for our volume. It's going to be pi times, and our limits are going to go with the y-axis because we're revolving parallel to the y. So that's going to be from 0 to 2. And our big R squared is going to be 3 minus y plus 1 all squared dy. Alright, and for our last example on this one, then we're going to do x equals 5. So again, our same basic sketch again. And still our same point of intersection at 3, 2. But now our axis of rotation's back over here at x equals 5. And so notice again we would have this big gaping cylinder that's formed when we start doing our rotation. And so again we need to find big R and little r. So big R is going to be the longest distance from my axis of rotation to the farthest away function. So here to here, that's going to be our big R. That's going to encompass everything. So that's going to be 5 minus, and then that function there rewritten as y plus 1. Little r is going to be on the inside part, and that's going to be this empty portion here. And so that distance for the empty portion is going to be 5 minus 3. All right, now we're ready to set up our integral again. And so let's see, we're going to have our pi integral, and along the y-axis again, so from 0 to 2, and we're going to have big R all squared minus little r all squared. So that's going to be 2 squared and then dy.